Here's a case study. We've seen 3 different designs of lists in homeworks 3, 4, and 5. So why did we have to go through 3 iterations? Well, homework 3 lists were simple, and their simplicity was splendid in a way, but they had an obvious flaw, which is if you wanted to query all the objects in a list, then it takes time proportional to the square of the length of the list. I'll be teaching this notation later and over the next 2 lectures, but big theta of n squared time means that the running time is roughly proportional to the square of the number of items in the list. The reason why we had to do this is we had this nth method that we had to use to look up each item in the list, and the nth method takes time proportional to I. So that was slow, and we knew we could do better than that. But in order to do better than that, we had to expose the nodes in the list to the application that uses them. So homework 4 fixed that, and homework 5 does as well. They allow an application to hold a node. So you can have a pointer to a particular node in the list, and you can move that pointer forward 1 step and query the item, and move it forward another step and query the item. And so now we can list an entire list in linear time. Which is a massive improvement. But in order to make those nodes exposed to the application, we had to make software engineering choices, which in homework 4 were deliberately done poorly, and in homework 5 were deliberately done correctly. But doing them right took a lot of careful thinking because there's a lot of subtlety involved. And today's lecture is going to be all about those subtle differences that make homework 5 well encapsulated and homework 4 not so good. So again, the homework 5 lists, S list and D list, are, as far as I know, well encapsulated. And the homework 4D list has flaws. And I will spend the rest of this lecture enumerating those flaws and how they got fixed in homework 5. Let's start with number 1. You might remember that part 2 of homework 4 was a question about how can you break the invariance of the list from an application just by calling the methods in a way that they were not intended. And there's several ways to do it, but here's the simplest one. What happens if we call L.remove_n with the homework 4 lists, but the node n is in the wrong list? What happens is that the wrong list size field gets updated. Now, one of the invariants of lists is that the size field is supposed to reflect the actual number of nodes in the list. And so with this one method call, we've broken 2 list size fields with 1 blow. So now the question is, how do you fix this? I'm going to give you 2 different kinds of answer. There will be one answer in terms of in terms of the interface, and there will be another answer in terms of how do we actually implement that improved interface. So looking at lists as an abstract data type with an interface, here's how you fix it. Well, remove and insert after and all these other methods should always update the right lists fields. But that's kind of the weak half of the answer, because the real question is, how do we actually make this happen? How do we implement this? Well, so the first way you might think of is to actually march through the list and look and check whether the node N is actually in the list L. But that's a really slow method. You should be able to remove things in constant time. If you have to march through a 1,000,000-item list just to check if the node is really there before you remove it, then that's too slow. That's not satisfying. So instead, what we did in homework 5 is every node keeps a reference to the list that contains it. Or specifically in homework 5, every node has a MyList field. And its purpose is to solve this problem. Any questions about any of this so far? Yeah. Mm-hmm. Yeah, well, if you wrote the remove code in any way I can think of, then your remove code ought to have somewhere in it a line of code that decrements the size after you successfully remove the node from the list that it's in. And unless you're actually checking by walking through the whole list to see if that node is there or not, that code's going to execute and change the size field of the wrong list. And I can't think of any way around it without making one of these corrections. Either the linear time checking through the list or adding this new field so that you can make this work. Other questions? So there's a second question about the interface that comes up naturally after we look at this first question, which is, where should the methods really be defined? Should they all be in the list class like they were in homework 4? And when you look at something like this, L.removeN, L doesn't actually matter. We're not going to look at what list L.removeN is called on. We're just going to look at what node it's called on, and you update that node's list. So there's no reason for remove to be in the list class. It makes more sense to put it in the list node class. So that's the question. Should insert after and remove and other methods like that be in the list class or the list node class? And the reason why this is a good question is because if we put things like insert after into the list node, then we completely avoid that first question. And as a result, we get a more elegant interface. So as we look over our methods and what they actually do, we discover that certain methods naturally belong in the list node class, but certain other methods still naturally belong in the list class. Depends on what they do. So for instance, in the list class, certain methods are just naturally belong there. IsEmpty should stay in the list class. Now, but also there are methods that do operate on nodes that should stay in the list class, because what they do is they create a node, but they don't take in a pre-existing node as an argument. Insert front creates a new node at the front of the list. And it's easier to find the front of the list from the list than from a list node. And likewise, the front method makes sense. That should be in the list class. But there are other things that make more sense in the list node class, like, well, in homework 5, you may have noticed there's an item method by which you look up the item that's in a node. There's, of course, a next method that finds the next node after a current node. And as I'm saying here, it makes a lot of sense to put methods like remove and insert after into the list node class as well. And this is just a more natural way to divide these things up, in my opinion. So this basically is the answer from the point of view of the ADT interface. That's the ADT interface fix. And then once again, the question comes up, how do you actually implement this? So the implementation fix relies mainly on the fact that, once again, each node has a mylist field. So whatever operation I do to a node, then I can go and update the list size field as well. After we call remove or insert after or whatever. Any questions about that? Yeah. Size is declared protected, that's right. Well, the list node is in the same package as the list. And I don't know if you recall that chart I drew some lectures ago of access, but protected access is weaker than package. So basically, if something has protected access, that means the subclasses can access it, but also anything in the same packages can access it. So protected is sort of the weakest protection short of being public. Everything that's in a subclass can access everything in the list, and everything that's in the same package can access everything that's in the list. So we put list and list node in the same package, and they can read all of each other's fields. Other questions? So let's come back to the question of, with the homework 4 lists, what are the ways that we can mess up its invariance? So I showed you one way, which is to mess up the size field. But here's what I think is the most interesting way. First of all, remove a node. Then insert something after the node you've just removed. What happens if you do that? Well, it depends partly on how you coded your remove method. But if you encoded it in the simplest, fewest lines of code way, then here's what happens. First off, you have this doubly linked list with x and n and y, let's say. And maybe there are things before x and after y, but I'm not going to draw them. And you remove n. So when you remove n, here's what happens. X and y now point directly to each other, but you still have a reference to n. And if you coded this in the simplest way possible, n still points to x and y. Now, not all of you might have done this. Some of you might have set these pointers to null, but you don't have to set the pointers to null for this implementation to work as specified. And if you didn't set the pointers to null, and then you try to insert something after n, then what happens next is it winds up looking like this. You've got x pointing forward to y, and you've got n pointing backward to x, and you've got a new node that you inserted after n, and n and that new node point to each other. And then the new node points to y, and y points to the new node. Y does not point back to x anymore. So we've made a mess here. We've now actually introduced a cycle into our loop that does not go through the sentinel. And we've violated the invariant that if x points to y, then y has to point back to x. Now, again, if you did implement your remove method so that it sets these two pointers to null, then your implementation won't mangle the list in this way, although it still will mess up the size field of the list. And if you call remove twice on the same node, that's another way to mess up the size field. Any questions on that? So let's look at how to fix this. First of all, from the ADT interface point of view, here's what we're going to do. After we remove a node, that node is declared invalid. This is how it works in homework 5. You do n.remove, and now n is considered to be an invalid node. And if you attempt to use n for any purpose at all, like calling insert after on it or calling remove on it a second time, it throws an exception. So we actually changed the, oh, yeah, question. And try to remove the reference that pointed to n? Uh-huh. Well, so what I've got is I've got this node object, and I've got some field inside it that I use to mark it as invalid. I say, put an X here if this node is invalid, but I do not change the reference that points to it. Which brings up a question. Why? Why do I change the node itself and not erase the reference to the node instead? Someone got an answer to that? Yeah. Right. You could have thousands of references to this list node, and there's no way you can hunt them all down and kill them all. I mean, in general, a program could have any number of those references, and there's no algorithm for finding them all, really. Unless you have access to the secret garbage collector or something. Question? That's the easiest way to do it, yeah. I'll write that down, actually. But well, I'll talk about why it throws an exception. But that's the decision I made for the homework 5 lists, is that if you try to use an invalid node for any purpose, then the method's going to throw an exception. I didn't have to make that decision. I could have just had the method always do nothing and fail silently. That would be okay for some situations. I'll talk about why I chose this particular choice. Let me tell you another reason, though, why we actually changed the item and not the reference that points to it. In Java, you pass n in by call by value. That means that whatever the original thing is pointing at, well, let's make it n. That means that when you call n.remove, n gets copied into a parameter called this, and the calling method doesn't even have access to n. It can't erase n. N was passed by value. We've got the copy. We don't have the original when we're doing the remove method. So we can't go and change this box. We don't even know where it is. So here's the implementation fix that I chose for homework 5. When you do n.remove, then the field n.mylist is set to null. And that's my standard way in homework 5 of marking a node as invalid. I just made a decision that the way you're going to identify invalid nodes in homework 5 lists is their mylist fields are set to null. I also, as a side effect, set the next and prev fields to null. And the main reason I do that is in case there's a bug and my encapsulation isn't as perfect as I hope it is, at least someone won't be able to go from here to here because n won't have pointers to nodes that are still in the list. It also helps Java's garbage collector to do that, but that's a subject you don't have to think about until the end of the semester when I actually teach garbage collection. And now, any attempt to do any operation on a mylist node, on a node whose mylist field is set to null, like remove it or insert after it, just throws an exception. The only thing you can do with a invalid node is call the isValid node method. That's the one method that won't throw an exception on an invalid node. And then applications are expected to just check whether their nodes are valid before they try to do something with them. Any questions about that? All right, another question that comes up is what happens if you walk off the end of the list using the next method or using the prev method? So if you're at the very last node in the list and you do n.next, there's no more nodes after it. So how should we respond to that? Well, here's what it looks like from the interface point of view. The answer depends on whether you're doing homework 4 or homework 5. In homework 4, we just return null. But in homework 5, I decided to do something different. I decided to return an invalid node instead. Why do I do that? Why do I prefer an invalid node to null? There are two reasons. One is that it provides consistency, I think. In the sense that calling next at the end of a list gives you the same result as calling remove on a node. In both cases, you wind up with an invalid node, and that makes sense. The second reason, I think the better reason, is suppose you do the next method and then you call a method on the result. Like maybe I have a piece of code that says, here's a node, I want the next node after it, and then I want the item that's in that node. Well, what happens when you do that? In homework 4, n.next is null, and calling an item on a null pointer gives you a null pointer exception. In homework 5, n.next is an invalid node, and calling item on an invalid node gives you an invalid node exception. Why is that better? Well, because it's differentiated. If you catch an invalid node exception, you know pretty much exactly what went wrong. But if you have a try clause that catches a null pointer exception, as you guys have all learned by now, there's 1,000 different things that could cause a null pointer exception. You don't know if it's because you went off the end of your list or because there's a bug somewhere else in your code. So it's nice to be able to distinguish invalid node exceptions and handle them separately from the null pointer exceptions, most of which you don't even know how to handle. So this eliminates ambiguity. These erasers need to be beaten and whipped. So there's, as usual, the question of how to implement this. Which, in this case, I chose convenience. I figure, well, if you're doing next in the last item of a list, and it's a D-list, and you're implementing it with a Sentinel node, why not just use the Sentinel node? That simplifies your coding, and then just say that any Sentinel node is an invalid node. And this is, you don't have to do it this way, but this choice simplifies the implementation. Now next always just follows the next pointer stupidly and doesn't worry about whether it's a Sentinel or not. If it's a Sentinel, it's still the right answer. It's an invalid node. Question, yeah? Yes, a Sentinel does have a next for the first item on the list, but if you call next on a Sentinel, you get an invalid node exception instead of the first item on the list. So your next method has to check if it's a Sentinel or if it's an invalid node and won't let you do anything with it. So you can get a Sentinel back, but you can't do anything interesting with it once you've got it. Yes? There's nothing wrong with that. I mean, you have to the other way to do it would be to actually generate a brand new invalid node in that circumstance, like construct a new one. And that's a little bit slower. If you want to save a few microseconds, this is the fast way to do it. But either way works. The Sentinel is an invalid node. Its myList field is set to null, and every method that you can call checks if the myList field is set to null and throws an exception if it is. So yeah, that'll always happen with a Sentinel. Yes, ma'am? Homework 4 or homework 5? Okay. Okay. Oh, but if you call, well, you don't call head from an application. You call front from an application. And what front does is it gives you the first node after the Sentinel. Yeah, but that's hidden inside the implementation. So come again? Anything that's inside the list or list node class can use the Sentinel however it wants. It's only applications outside the list class that I'm talking about. They can't use the Sentinel to do anything interesting. So that's why, yeah, if you have a Sentinel and the application tries to do anything with it, you want it to return an invalid node exception. You're welcome. Yes, sir. The Sentinel does not know what list it's in, right? Fortunately, it never needs to, because you can't remove anything. You can't remove it from the list. You can't call insert after on it. You can't call anything that changes the size of the list on a Sentinel. So the Sentinel doesn't need to know what list it's in. And that's convenient. If that were not the case, I'd have to have two separate fields, like a myList field and a valid node field. But in this case, I'm just saving memory by only using one to do both jobs. Yes? What's... the point of having a Sentinel is the same thing it always is making the implementation a few fewer lines of code. So it's not something you expose to the outside world at all. You don't want the people using your list class to know whether you're using Sentinels or not. It's only there for the convenience of you, the programmer, to have a few fewer lines of code. That's it. Other questions? Okay. The final point is how do we access an item? You may have noticed that I changed this between homework 4 and homework 5. So here's what the interface looks like. In homework 4, each node's item field is public. And so when you want to change the item or read the item, you just go in and you read or change it directly. Easy. Homework 5, I was not so kind. I forced you to go through methods if you're an outside application and you want to get at that item. So now the item field is protected. And applications now have methods that they must use to get at that field. If you want to know what the item is, you call the item method. And if you want to change it, you call the setItem method. Why did I make that change? The big reason is, well, now I'm returning Sentinel nodes in this homework as invalid nodes. And I'm also have invalid nodes like nodes that were removed from a list. Once someone removes a node from a list, I don't want them to be able to store things in that node anymore. I don't want people to store things in Sentinel nodes either. Any attempt to store an item in a Sentinel node or in a node that you've removed from a list gives you an invalid node exception. You can't use that node to store things anymore. And why do we do that? So that you can change your list implementation without breaking the applications that rely on it. Like, for instance, suppose that an application developer finds out that your lists that allow them to save information in nodes that they've removed from the list or in Sentinel nodes, and they start writing their code to depend on that. And then you go and change your code to an S list, and you're not using Sentinel nodes anymore. Or you do something with the removed nodes internally that changes their contents. Now, you've broken the person's application because they were depending on these weird quirks of how your data structure works that has nothing to do with lists. And this is actually really common. It's important not only that your ADT do what it says it will, but ideally, ADTs should never do more than the documentation says they will. Or you run the danger of having programmers come to depend on the quirks of your implementation, and then you're locked into that implementation forever. Like you're locked into having Sentinels, for instance. Now, this kind of thing is far more common in the real world than you would believe. Here's a book on software engineering. It's the most famous book on software engineering called The Mythical Man-Month by Frederick Brooks. And although software engineering is usually kind of a dry topic, this book is really readable. It's actually hard to put down. It's the most interesting book on the topic I know of. And here's one of the things that Brooks says from his experience leading large software teams for several decades. Invalid syntax, like storing stuff in a Sentinel node, always produces some result in a policed system. That result is an invalidity indication and nothing more. In an unpoliced system, all kinds of side effects may appear, and these may have been used by programmers. When we undertook to emulate the IBM 1401, which is a 1960s era computer, on System 360, which is a 1970s era operating system, for example, it developed that there were 30 different curios, side effects of supposedly invalid operations, that had come into widespread use and had to be considered as part of the definition. The implementation, meaning the computer, as a definition, overprescribed. It not only said what the machine must do, it also said a great deal about how it had to do it. And so they had to do a great deal of work to make their emulator work. So by ensuring that your ADT does not produce any result other than what it's supposed to, you ensure that programmers won't come to rely on those results and lock you into one particular weird way of doing it. Like, suppose that I allowed you to go take a node at the end of the list, n, and do n.next.next, skipping over the sentinel node, and you would wind up at the beginning of the list. Then suppose you wanted to change your dlist implementation so it used singly linked lists instead. Now you would have to fix your S-lists so that when you do n.next.next from the end of a list, you wind up at the beginning of the list. And that would take some weirdness. Question? So unfortunately, that's a hard question. The question is, how do you write your program so that this doesn't happen? And programs, in a sense, are unanalyzable. It's a matter of you try your best. There's no guarantees. You usually can't prove that your code won't have these kinds of quirks. But if you at least find out about them or know about them, you try to kill them and design things, for instance, like if you have sentinel nodes, you make sure that no one can use those sentinel nodes. You do the best you can. But you can actually prove that there's no perfect solution to this problem. It's a mathematical fact. So anyway, the lesson of this lecture is that design decisions in encapsulation can be very subtle, and you have to think a lot about it, and that encapsulation is a much harder thing than it appears at first. So our design decisions for the homework 5 lists, I think, are well encapsulated, and those will carry over to the tree data structures you'll work with in a later homework. See you Friday.